Welcome back to our mathematics videos. Today we're going to have a look at a small example for the Lagrangian multipliers theorem. So we'll start with a very easy optimization problem. We'll just take a simple two-dimensional function and constrain it to a domain that is a circle, and then we'll try to optimize the function over that circle. So the problem that we are going to tackle is minimize the function f where f of x1, x2 is defined as x1 plus x2. And we're going to constrain this to the feasible set described by the function x1 squared plus x2 squared equals 1. So in other words, our function f is given by x1 plus x2. That's obvious. And here our function h of x1, x2 is given by x1 squared plus x2 squared minus 1 equals 0. Okay, so this is our optimization problem. We want to find candidates for extreme points of f on that circle defined by x1 squared plus x2 squared equals 1. So a circle of radius 1 around the origin. Let's remark that. So this feasible set here, f is a circle of radius 1 around the origin, the 0 vector. So how are we going to solve that? Well, the first thing we need to do is set up the Lagrange function. So we have the function L that depends on x1, x2, and also on a Lagrangian multiplier that we are going to call Z. The function h maps to the real numbers, so we just have one real Lagrangian multiplier to consider. Okay, so this function is defined as you know, f of x1, x2 plus z times h of x1, x2. So in this specific example, the Lagrange function is x1 plus x2 plus z times x1 squared plus x2 squared minus 1. And now what we need to do is to set up the gradient of that function. So to find candidates for extreme points, and remember, we're always just talking about candidates. The conditions that we have derived so far are necessary. So every extreme point satisfies those conditions, but they're not sufficient. So not every point that satisfies these conditions is necessarily an extreme point. Okay, so those are just candidates again. If you want to find candidates for extreme points, what we have to do is we have to set nabla of L, x1, x2, and z equal to 0 and find the points that satisfy this condition. So what do we get if we differentiate the Lagrange function here? Well, differentiating with respect to x1, so here's the function again. Differentiating with respect to x1 gives us 1 plus 2 z x1 Differentiating with respect to x2 yields 1 plus 2 sed x2. And finally, remember, we also have to differentiate with respect to lambda. So that will yield x1 squared plus x2 squared minus 1. Okay, so that's our Lagrange function here. And this needs to be equal to 0. So as you can see, this gives us 3 equality constraints for the 3 unknowns x1, x2, and z. And we have to solve for those. So how do we do that? The easiest thing we can do is probably use the first 2. So from rows 1 and 2, we can easily solve those for x1 and x2 respectively. So what we get here is x1 equals minus 1 over 2 z. And let's just keep in mind that z must not be 0 for that to hold. x2 equals minus 1 over 2 z as well. And again, z must not be 0. And then we can use those on row 3. And that gives us minus 1 over 2z squared plus 1 over 2z minus 1 over 2z squared minus 1 is 0. So in other words, 1 over 4 times 1 over z squared plus 1 over 4 times 1 over z squared equals 1. Or z squared equals a quarter plus a quarter, and that's 1 over 2. Or z equals plus or minus 1 over the square root of 2. Okay, so if that is the solution for z, then obviously we can compute the corresponding values for x1 and x2 quickly. So x1 is minus 1 over 2z. And that means what we get is plus or minus the square root of 2 over 2. And the same holds for x2. Again, that's plus or minus the square root of 2 over 2. Okay, so specifically the solutions that we get is 2 solutions so far. One is for a positive value of z. So if we use a positive value of z here, 1 over square root of 2, then the corresponding values of x1 and x2 are negative. And that means what we get is the solution minus square root of 2 over 2 minus square root of 2 over 2 and 1 over square root of 2. So that will satisfy the equations. And the second solution we get is square root of 2 over 2, square root of 2 over 2, and then minus 1 over the, minus 1 over the square root of 2. Okay, so those are the possible solutions here. One last thing that we have to consider is the case z equals 0. Well, if that is the case, then our equations, let's have a look at those again. What form would they take? Well, if z equals 0, then let's have a look at these equations here. You can see the first one would then become 1 equals 0. Second one as well, 1 equals 0. And those are obviously contradictions in itself. So this is not possible. So the equations become 1, 1, well, and the last one just stays the same, x1 squared plus x2 squared minus 1 is 0, 0, 0. A contradiction. Okay, and that means we don't get an additional solution for that case. No additional solution for z equals 0. So we are left with the two solutions that we already computed. So that's it. And that means we have two candidates for those extreme points. Minus square root of 2 over 2, and minus square root of 2 over 2, and square root of 2 over 2, and square root of 2 over 2. So those are the candidates. Candidates for extreme points. So we have square root of 2 over 2 times 1, 1, basically, and the other one is minus square root of 2 over 2 times 1, 1. So those are the x1 and x2 coordinates of our extreme points. And of course, we still have to find out which of these are minima or maxima. The theorem doesn't tell us anything about that. The condition holds for all extreme points. And obviously you can just find that out by substituting those into f. By substituting into f, we learn that minus square root of 2 over 2, 1, 1 is a candidate for a local minimum. While plus square root of 2 over 2, 1, 1 is a candidate for a local maximum. Okay, but we later talk about sufficient conditions for those points to actually be extreme points as well. And it will turn out that in this example, we could also just apply those sufficient conditions. But that's going to be part of one of the later videos. So for now, we only have those candidates. But you now know how to compute those in this setting. So that concludes that first example. And we'll also have a look at a more abstract example, an application in economics in one of the next videos, before we move on to more general settings. Thanks for your attention.